Alright, so this is section 2.7 and we're going to discuss nonlinear inequalities. So an inequality that can be put into one of the forms where we have less than 0, greater than 0, less than or equal to, or greater than or equal to, is a polynomial, where f is a polynomial function, is considered a polynomial inequality. Okay, so I included this from my previous notes that I had last year, and this is a simple procedure for solving polynomials inequalities. So first you want to begin by expressing the inequality in the form of less than 0 or greater than 0, where f is a polynomial function. We're going to begin by solving the equation for f of x equal to 0, and we're going to get real solutions are going to be called boundary points. We're going to locate these boundary points on a number line, and we're going to divide the number line into into intervals, not equal intervals. Then we're going to choose a test value, so values in between these boundary points, and I'm going to determine if it is part of the solution or not. Then we're going to write the solution set, and we should be really good at this point in interval notations. This procedure is valid if less than is replaced by less than or equal to, or greater than is replaced by greater than or equal to. However, if the inequality involves those symbols, include the boundary points, the solution set should be brackets, right? I'm about to show you what I mean. Okay, and your notes say the following. You want to get 0 on one side by itself. You're going to solve as if f of x is equal to 0, and solutions, I like to call them boundary points. So let's change that, boundary points. Okay, then you're going to use these terms to determine test intervals, and then you're going to choose one point from each interval by plugging it into the inequality. If the statement is true, then the range is part of the solution. And then we're going to write the solution in interval notation. Okay, so please note that it's boundary points that I will be using instead of the word key terms. Alright, so here's our first example. Okay, so remember, we want to bring the polynomial to one side of the equation so that we have this less than or equal to 0. And then we want to solve the polynomial as if it equals 0. And then I'm going to go ahead and factor it. So we have x minus 4 times x plus 3. Good. So my boundary points are what? X equals 4, x equals negative 3. Okay, so let's go ahead and plot those points. Are we allowed to equal these points according to the symbol on our given? Am I allowed to equal those solutions? Yes, I am. Okay, so that's when you do closed circles. You have open circles if this would have said less than, or if this would have said greater than. So at 4 and negative 3, I'm going to put closed circles. So I'm going to estimate that 4 is right here, and negative 3 is right here. And now I just separated my number line into 3 intervals. And I'm going to pick anything in between these intervals to test. Okay. What my first slide said to you was look at the signs. Okay. If I substitute 0 into here, I'm going to end up with negative less than 0. Is that true? If I put in 0 here, is 0 less than 12? Yes, it works, right? So that's part of our solution set. So here we can go ahead and color this in. This is my solution. I have 2 other regions that I could test to determine is it part of our solution. So 10 and negative 10 is what I'm going to choose to test. What we could test is signs, positives and negatives. Okay, you follow me? So if I put a positive here, hypothetically 10, and then minus 10, that's still going to come out positive, right? Because I'm going to have 100 minus 10, which is 90. Is 90 less than 12? No. Okay. And then I could do the same thing with a negative. I'm still going to end up with a very, very large number because I'm squaring that negative 10. That's 100. That will never be less than 12. So my only solution set is here. And how do I write that in interval notation? Because I'm including negative 3, that's a bracket. And we're going up to 4, and because I'm including 4, that's a bracket. Alright, so here's another example. Remember, you always want to isolate your polynomial function. So I'm going to begin by bringing that 15 over, and we're going to have x cubed plus x squared plus 15x plus 15. And remember, we're hypothetically solving it as if it were equal to 0. It doesn't equal 0, I'm pretending as if it does. How can I factor this? Okay, by grouping, good. So I'm going to group the first two, factor out an x squared, and then I get x plus what? 1, good. What can I factor from the right side? 15. And then I get x plus 1, good. And now I'm going to group x squared plus 15 and x plus 1 equals 0. So my solutions, here I get negative 1. And here, what happens here? Okay, good. I'm going to get negative 15 on this side. I'm going to take the square root of that. When I do that, I get the square root of a negative. So it's going to be x equals plus minus I root 15. Are those real numbers? It's not part of our number line. So that's not going to be part of my solution set. So the only boundary point is negative 1. So let's go ahead and find negative 1 on our number line. Okay, so here I went ahead and I plotted my solution, my real solution. And now I have to determine, is my solution to the right or to the left? I like to pick 0 when it's in the test interval. I think it's easier. So let's take a look at the given. Let's substitute 0 in here. 0, 0, 0, 0. Is 0 greater than negative 15? Yes, it is. Okay, so this so far includes our solution. Let's test negative 2 or anything that includes a negative number. Okay, I'm testing the sign because I think it's easier to test the sign. So let's say negative 2 cubed, negative 8. I'll show you what I mean in just a moment when I talk about rational ones. When I square negative 2, what happens? Plus 4. And then 15 times negative 2 is plus negative 30. Is that greater than negative 15? No. We're going to get negative 34, and negative 34 is not greater than negative 15. So our solution set, let's put in interval notation. We're including 1, so that's going to be a bracket, and we're continuing towards positive infinity. Do I put a bracket or parentheses over infinity? Parentheses, because it's not bounded. Good. Alright, so let's take a look at this. A rational inequality is an inequality that can be put into one of the forms. F of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0. That's what this last point should say. Okay, where f is a rational function, an example of a rational inequality is the following. So here's our example. 3x plus 3 over 2x plus 4 is greater than 0. This inequality is in the form of the polynomial is greater than 0, where f is the rational function given by the following. Okay, we can find the x-intercept of f by setting the numerator equal to 0. Remember, I was saying in the previous section, if I have a fraction equal to 0, and I'm trying to isolate my variables, and I multiply the bottom by 0, it's always going to 0 out, right? Therefore, the numerator, if I have fraction equals 0, is always going to have your zeros, your x-intercepts, or your solutions for x. So I'm only going to set the numerator equal to 0 so long as I'm in this format, fraction equals 0, when I set this equal to 0. Now let's solve for x. We get negative 1. We can determine where f is undefined by setting the denominator equal to 0. So think back to what we did yesterday. Whatever makes your denominator undefined, remember those were the exclusions or our vertical asymptotes. So here, we set the denominator, this should say equals 0, and we're going to get x equals -2. So our interval, I'm going to show you that interval solution set in just a moment. When I graph this, I have a vertical asymptote at -2, right? I have an intercept at -1, and then I create my rational curves. I can also find my horizontal asymptote here would be 3/2. Do you guys agree? Okay, so that 3/2 would be right here. Then create your rational curves. Okay, we could also use our number line to graph here by picking test points. So my test points are going to happen at -2, -1, and here I'm going to determine where are my solutions. And then here we can clearly see that our solutions are only happening from here to here and here to here on our number line. So in interval notation, this should read from -infinity to -2 union -1 to +infinity. So I had multiple test points on my number line. Let me just duplicate that number line again. I had a test point at -2, open circle because we weren't including it, at -1, and let's say here's 0, here's +infinity, here's -infinity. So notice that this time I divided my number line into 1, 2, 3 regions, and then I tested. My only solutions are going to come up here and here. And I can also see that in the rational graph, where the values from -2, -1 should be excluded. Right? Do you see that? Alright, so let's take a look at this rational inequality, and the instructions say to solve and graph the solution set. So again, first begin by finding your x-intercepts. Okay? We get set your numerator equal to 0. So 5x minus 2 equals 0, and what do I get? 2/5. And then I want to determine where is the denominator undefined on my number line. Remember, this is going to create our boundary points. Okay, so we're also setting the denominator equal to 0. What do I get? -1/3. So now let's take these points. Are we allowed to equal these values? No, we have an open circle because of this inequality, right? So on the number line, let's graph 2/5 and -1/3. Okay, so here's my number line. I broke up 0 to -1 into 3 parts and 0 to 1 into 5 parts. 1, 2, 3, 4, 5. At -1/3, open circle. At 2/5, open circle. So now I have, let's count, one region to test, another region to test here, and another region to test here. I want my answer in interval notation. So let's go ahead and start testing. I think it's easy to test sines. Okay, I'm going to pick something from here. It's obviously going to be positive because anything to the right of 2/5 is positive. So let's test positive sines. Let's see what that does to our given. If I put a positive in the numerator, say 1, because that might be easy for you to see, your numerator is going to come out positive, your denominator is going to come out positive. Do you guys agree with me? Okay. So a positive over a positive is going to come out positive. Is a positive greater than 0? Yes, always. So that's my solution, and that's what I mean by testing sines. Okay, if you don't understand the concept of just test the sign, go ahead and substitute it. 5 times 1 minus 2 over 3 times 1 plus 1. Is that greater than 0? So we get 5 minus 2 is 3, and 3 plus 1 is 4, so we get 3/4. 3/4 is greater than 0. Works. Okay. Now I want to test 0. When I put 0 in, I'm going to get -2 over 1 because this is going to reduce out. Do you agree? Is -2 over 1 or a negative greater than a positive or greater than 0? No, that does not have our solution. Now I want to test a negative. Okay, so now I'm going to test a negative here. It could be -1, or it could just be a hypothetical negative sign. When I put in a negative in here, this is going to come out negative, and this whole top part is going to be negative. It doesn't matter what number I put in there, because 5 times a negative is negative number, whatever number that is. Minus 2 stays negative. So my numerator is negative. That sign is negative. Let's take a look at the bottom. 3 times a negative. Let's exaggerate that negative. Let's make it negative 10. Plus 1 is going to stay negative. A negative divided by a negative is going to come out positive. Is a positive number going to be greater than 0? Yes, always. Okay. Do you get the concept of testing signs now? I think it's easier to test signs instead of substituting a value, because if you're testing signs, you're hypothetically plugging in a lot of numbers, and it's easier to answer this question. So it includes our solution. Our solution is here. Let's say you don't understand the concept of testing signs. Let's go ahead and plug in negative 1, okay, to make sure that you got the concept. So 5 times negative 1 minus 2 over 3 times negative 1 plus 1, and let's simplify that. Negative 5, negative 7. Here I get negative 3 plus 1, negative 2. A negative over a negative, 7 over 2. 7 over 2 is greater than 0. So that works. So yes, you can pick points and test it, but did you just see how much more work I just did? That's why I think it's easier to test signs. You will solve the problem a lot quicker. So just take a look over here. All I did was think about, what do my signs look like? What happens? Is it greater than 0? The answer is yes. That's part of my solution. So let's go ahead and write our interval notation for our solutions. So we're starting at negative infinity. Remember, we always write it from left to right. So negative infinity to negative 1/3. We're not including that, so that's parentheses. Then we have a union from 2 over 5 to positive infinity. I was just asked what would happen if we were plugging in negative 1/5. Well, negative 1/5 is going to be over here. It's not in the interval that's here. So when I'm thinking of the negative numbers that I'm plugging into the given, I'm thinking of numbers in this interval, excluding the numbers that are in this interval, because technically I already tested in here when I plugged in 0. And then what happens to the right of 2/5. So remember, when you're testing the numbers, to think of numbers in that interval and the signs in that interval. Alright, so let's take a look at another example. Solve and graph the solution set. And this one looks different. Okay, what's different about this? It's not less than 0, it's not greater than 0. So what do you think I'm going to do? I need to set it equal to 0, right? Because otherwise I can't find my boundary points from the top and the bottom. Therefore, what I'm going to do is I'm going to bring it over and get a common denominator. Okay, so I brought my 3 over. Subtracted 3 from both sides. Now I need a common denominator. The common denominator is this 4x minus 1. So I'm going to multiply negative 3 by 4x minus 1 over 4x minus 1. And when I do that, I'm going to distribute that negative 3. And now I have my common denominator, so that can stay in the bottom, 4x minus 1. From the given, we got 8x plus 2. Distribute the negative 3. Negative 12x plus 3. And now I have something that's starting to look like our first problem. Okay, now I want to combine like terms. So 8x minus 12x is 2 plus 3. And now I can find my boundary points. So let's go ahead and find our boundary points for this. What do I do? Set the denominator and numerator equal to 0. So negative 4x plus 5 equals 0. Subtract 5, divide by 4, x equals negative 5 over negative 4, which makes it positive 5 over 4. My next one, 4x minus 1 equals 0. Bring 1, divide by 4, x equals 1/4. So now I have my two boundary points, 5/4 and 1/4. Let's go ahead and create our number line and plot our boundary points. Alright, so here's our number line, and I have negative, I broke it up into quarters, the number line, and I'm plotting 1/4 and 5 over 4. I have open circles because we did not include that because we had a less than symbol and a greater than symbol. We did not have less than or equal to. Okay? Now I have testing regions. Here I have my negative solutions. Here I have, if you wanted to, you could put 1. And here you have values that are greater than 5/4 with positive signs. So be careful when you test over here because you have overlapping positive signs. Alright, so let's test our signs. I'm going to begin by testing values that are over here, specifically negative values. And in your mind, start exaggerating negative signs. If in the top, hypothetically, you put in a negative value, do you agree that it will always come out positive? The numerator will always be positive. It doesn't matter what that sign is, because a negative times a negative, positive plus a positive, positive. So your numerator, when you're testing our test of a negative, I'm going to put test neg, our numerator is going to come out positive. Now let's exaggerate that sign in the denominator. 4 times this exaggerated negative, negative, minus 1, negative. So the denominator is negative. Positive over a negative will always be negative. Is a negative less than 0 all the time? So this includes our solution. That's what we're interested in. Now I'm going to move to the right. Exaggerate a positive. So now I'm testing a positive. I'm specifically testing values to the right over here. Okay? So exaggerate that number. I know that that's going to be to the right of 5/4. Then we're going to come back to over here and see what's happening. Okay, so now I'm testing my positives. So test the positives. So when I put in a positive over here, I get a negative. Doesn't matter what I exaggerate that number to be. -4 times whatever number I pick to the right of 5/4 will always be positive. Negative, excuse me. +5 doesn't matter what I picked because I exaggerated my number. So let's say I picked 10. That's -40 plus 5, still negative. So my numerator will always be negative. Let's test our denominator. An exaggerated number, say 10, will always make this positive because you're only taking one away. So now you have a negative over a positive, and a negative over a positive is still negative, and a negative will always be less than 0, so far we've established that this is our solution. Now I have to just figure out, does this include my solutions or not? So test 1, because 1 is a quick number that you can just plug in and check real quick. So -4 times 1, -4, plus 5, positive. Okay? 5/4 is 1 1/4. Okay? So 1 is between 1/4 and 5/4. So now I'm testing in between my boundary points to determine, is this third interval that I have yet to test part of my solution? So now I don't have 0 in there to test. Therefore, and notice that if I would have picked 0, I would have got 5/-1, and that's true, so that's part of our solution. Wherever 0 is, it's always easy to test, whichever boundary or whichever interval it's falling into, so always pick the 0 to test. But 0, unfortunately, is not in here. 1 is, 1's easy. Okay, so again, here I went ahead and I plugged in 1, and we end up with a third when we simplify this. Is that less than 0? No. Okay, it's not less than 0, so this is not including our interval. So our solution is set. Now all I have left to do is include my solution interval. So from -infinity, because remember we're going from left to right, to 1/4, not including that point, so union, to 5/4, not including that point, so that's parentheses, towards positive infinity.